Hello everyone. So today is a very important topic, and it's probably the biggest topic in maths, full stop, is integration, of course. Um, Integration is an incredibly large topic, and it's almost impossible to learn everything about integration. Yeah, so. Um, it's full of surprises always. Of course, at school you learn like the basic tricks, just with a few extra tricks at Compos, and then you'll learn a lot more in university. But yeah, overall. So calculus part two, welcome, and are we? It is, yes, I am recording. Lovely. So integration. Integration is the opposite of differentiation. So when you have um, if you have you, if you know, if you know, you know the derivative, so f dash of x, what is f of x? So this is the question we're trying to answer. And some of them are really simple. So example, if f dash of x is equal to 3x plus 2, then you could quite easily figure out that f of x is probably something like 3 over 2x squared plus 2x, because the derivative of that function is that. However, this is not a unique solution, because what if you say plus 3, right? The derivative of this function is also 3x plus 2, or plus 4. So the derivative of this function is also 3x plus 2. So we say we we call this the primitive function, or the antiderivative, and we say plus c, where c is known as the constant of integration. Because whatever c is, it is a constant, and the derivative is going to be 0. So this expression describes all the possible functions that have this derivative. So it describes all possible functions with derivative f dash of x equals f dash of x equals 3x plus 2. And if you sketch that graph, it looks something like this. So 3x squared plus 2x, so that's b over 2/3 minus 2/3. So minus 2/3. So it's a series of parabolas for different values of c. This is a series of parabolas. So all of these parabolas are solutions, are all, yes, okay, for different values of c. So for example, this would be c equals minus 3, c equals minus 0.2, c is 1, c is 2, c is 3, etc. So just different values of c. I hope you understand what I mean. And you can see that the gradient of all of these functions, what I have drawn, they all have the same gradient at the same point. So if you take this point, for example, this point, and you draw down, they all have the same gradient at that point. And that's the idea. Because if you know the gradient function, what is the function? There are multiple possibilities. Okay. Sometimes you're asked to find the particular solution that passes through a given point. then you would say, well, if there's a given point, P, there's only one of these curves passes through point P. Find f of x that passes through point P. In that case, you substitute the coordinates of point P, coordinates of P into equation and find x, and find C. Sorry, find C, and that way you can work it out. Okay, so let's do some practice. You're given that the derivative of a function. So by the way, today's problems are very similar to the ones in the assignment. So you would benefit heavily from this webinar if you're struggling with the assignment, for example. You're given that the derivative of a function is that. So basically what it says that f dash of x is 2x minus 1/4 square root of x plus 1. What else do we know about f? Well, we know that f of 4 is 0. F of 4 is 0. Okay. We call that boundary conditions or starting conditions, depending on that boundary condition. Now, df. So if we know the derivative, we can write it as 2x minus 1/4 x to the power half plus 1. And we need some formulas. Of course, the integral of x to the power n dx is the opposite of the derivative. So x to the power n plus 1 over n plus 1 plus c. This is the formula that we're going to use. And here we would write. So if f dash of x is this, then f of x is the integral of 2x minus 1/4 x to the power half plus 1 with respect to dx. And the integral of that, so it's 2 multiplied by x squared over 2 minus 1/4. So x to the power half, half plus 1. So it's going to be x to the power half plus 1 over half plus 1, so 3 over 2. And then plus just x and plus c. Now let's simplify that. F of x is x squared. Now this becomes 2 divided by 12, 1/6 plus 1/6 x to the power 3 over 2 plus x plus c. Because f of 4 equals 0, we can do f of 4, we can substitute 4 into this equation, and that becomes 4 squared plus 1/6 x, 4 to the power 3 over 2 plus 4 plus c, and that must equal to 0. Therefore, c is equal to negative 16, negative 4, negative, so 4 to the power 3 over 2, that's 8. So 8/6, and that's 4/3, 20, 60, negative 64/3. And therefore, we can write f of x is equal to x squared plus a 6th x to the power 3 over 2 plus x. Yes, thank you. You are correct. It is negative. I made a mistake. So that's going to be plus. And Okay, so that's not 64, that's 60 minus 4, which is 56. Negative 56 thirds. Okay, 56 thirds. Right, we found f. And then it says that dg dx, so g dash of x, the derivative of g, is f of x. Oh, so that is x squared, sixth x 3 over 2 plus x minus 56 thirds. So that means g of x is the integral of that thing, 1/6 x 3 over 2 plus x minus 56 thirds dx. So g of x is equal to x to the power 3 over 3 plus 1/6 x to the power 5 over 2 over 5 over 2 plus x squared over 2 minus 56 thirds x plus, well, we've used c already. I don't really like using other letters like D, so because we already used D, so and E has a different meaning. So I prefer to stick with C1, for example. I say C1. And here, because I know that G of 4 is 2, that means G of 4, that's, well, just 2. 2 equals 4 cubed, that's 64 thirds. Then this is 3/15 plus 1/15 multiplied by 32 plus 16 halves, that's 8, minus 56 over 3, so it's 112 thirds. Oh no, it's 224 thirds. Is it? Yes, 224 thirds plus C1. So C1 is, what do I do here? Well, do we have to multiply everything by 15? It's very unsettling. Sorry, I'm just going to use a calculator for now. 64 thirds. I'm sure you are all proficient in working with fractions. There's no point of me 224 thirds, 226 fifths, and hence the answer g of x is equal to 1/3 x cubed plus 1/15 x to the power 5 over 2 plus a half x squared minus 56 thirds x plus 226 fifths. That is the solution. Okay. The next question is the following. Sketch the curves, label all the points of intersection, and calculate the area enclosed between the two curves. I've just reached the minus sign again, have I? Have I? I have. Oh, silly me. Okay. Thank you for pointing that out. Pointing that out. So C1 is going to be different. So that's a minus. And C1 is going to be slightly different. So 2 minus 64 thirds plus 32. So 742. 742 fifteenths. So 742 fifteenths. Okay, thank you for that, Luke. Right, moving on. Sketch the curves y equals x squared minus 2x. The easiest way to sketch quadratic curves is by completing the square. So I'm going to write it as a completed square. And this is x minus 1 squared minus 1. And we can straight away sketch that. So this is a standard parabola. Shifted by 1 square to the right and 1 square down. So let's call this 1, 2, 3, 4. 1 square up, 1 square down. And then it goes through 2, 4, 3, 1, 2, 3, 4, 5. So 2, 4, 3, 4, 5. All right, for the second one, x is equal to y squared minus 2y. You probably have never seen anything like that before. Now, how on earth do you sketch that? Well, there are different ways to do this. I think the easiest way would be to complete the square again. So x is equal to y squared minus 2y plus 1. That's a completed square, minus 1. And then you take that. So x minus 1 is equal to y minus 1 squared. And then you take the square root. So y minus 1 is equal to plus or minus square root of x minus 1. So y is plus or minus square root of x minus 1 plus 1. That's one way of doing it. Not the easiest way, but it's workable. So there are two curves here. First is y equals square root of x minus 1 plus 1. So that is a curve. So you should know the square root curve by now, square root of x curve. So it shifted 1 to the right and 1 up. So 1 to the right and 1 up. So this is like this. 2, 4. And the other one is minus. So it's the same graph, but the other way around. So it goes like this. Okay. And you need to find the area enclosed. So you need to find that area. Okay. So there's a lot of stuff going on in here. Well, first of all, you need to find this point. This point is obviously 2, 0. This point is 1, 1. 1, 1. And then you need to find this point. Oh, this point is 2, 2. 2, 2. So this point is question mark. So to find this point, we're going to make them equal to each other. So y is equal to x squared minus 2x, and x is equal to y squared minus 2y. Doesn't really matter how you do it. I suppose. I'm making so many mistakes today. Yes, and it makes life so much easier. Okay. Very quickly. I reached the limit. Okay. Okay. That's doesn't make any sense. Okay. It is +1, and so this is x plus 1 and x plus 1, and then -1. So +1 plus 1. So square root of x plus 1. So it's shifted to the left. Now we can redraw this. So the first one was 1 and -1. 1, 2, 3. Oh, 1, 2, 3. Okay, and the second one was square root of x plus 1. So it's shifted to the left and up. So it starts from here. It starts 1, 2, 3, 1, and 1, 2. So it goes like this. And this looks like right. One thing to notice that these two functions are sort of inverses. Y plus 1, y plus 1, right, and -1, x plus 1, no, it's y minus 1, y, it is y minus 1, no. Y minus, because it's y squared minus 2y plus 1, and then -1, so y minus 1. Y minus 1 is plus minus x plus 1, plus minus x plus 1, minus 1. Okay. And you need to find the area enclosed between the two curves. Sketch the curves, label all points, sketch the area enclosed between the two curves. Well, so enclosed between the two curves, they would mean that is this bit basically. Still not easy, but doable. So how would you approach that? Well, you need to find the points of intersection first. To find the points of intersection, here they are. So let's label them. This one and this one. This one. This is quite harder than the one in the assignment. So, but hopefully you'll find it useful. So that's 0, 0. This is obviously 3, 3. 3, 3. You can check that. And then we're looking for these 2 points. These 2 points will be symmetrical, so we just need to find one of them. And to do that, we can use we just solve. So y equals x squared minus 2x, and x is y squared minus 2y. So let's substitute one into the other. Let's do x. So let's substitute y. So x is equal to, so substitute this into that one. X is equal to x squared minus 2x squared minus 2x squared minus 2x. So x is equal to x to the power 4 minus 4x cubed plus 4x squared minus 2x squared plus 4x squared. Okay, so x to the power 4 minus 4x cubed plus 6x squared minus x equals 0. So x is either 0 or x cubed minus 4x squared plus 6x minus 1. 4x squared, 4x, yes. Thank you for pointing that out. I didn't know what was going on with me today. Very unattentive. Plus 2x squared plus 3x. It has to be 3. Of course it has to be 3. I would have spotted this error, but it would probably have taken me quite a bit of time. 3 is equal to 0. And now we know that 3 is also a solution. 3 is a solution. So we are going to use the factor theorem. Well, we will kind of already use the factor theorem. So we divide by, so x cubed. And to divide by x, we divide by x minus 3. Instead of like dividing it as you were taught in school, I'm going to do it slightly differently. I'm going to say x cubed minus 3x squared, and we have minus 4, so minus x squared, because minus 3x squared minus x squared is minus 4x squared. Now to do this, we need to have plus 3x here, because we want to factorize. I'll show you in a bit. So this is by grouping. Okay, plus 3, but we have 2x, so it's minus x plus 3 equals 0, equal. And now we can factor each group. So this is x squared, we can take out, and it's x minus 3, minus x minus 3, and minus 1, x minus 3. Of course, now we can take x minus 3 out, and we are left with x squared minus x minus 1 equals to 0. So that means x equals 3, or x squared minus x plus 1 equals 0. So x minus a half squared minus a quarter plus 1 equals 0. So x is equal to a half plus minus 3. It doesn't make any sense. Where have I gone wrong? Okay. I think I need to sketch them. Y equals x squared minus 2x. Yep. And x is equal to y squared minus 2y. Minus 1, of course. Go to 5 over 2. X is this. So we have two values. Okay, this is way harder than I anticipated. They way more, not harder, but way more So this point is x is a half plus root 5 over 2. And this point is x minus a 1/2 minus root 5 over 2. Now we can, what do we want to do? We want to find the area enclosed. And I'm going to split it into pieces because so first of all, I'm going to split it like this. I'm going to find the area under this curve. Oh, yes. So first of all, I'm going to find this area. Area 1. This is A1. A1. And that would be the integral of the top line, which is square root of x plus 1 between limits 5 over 2, 1/2, 1/2 minus root 5 over 2, and 3 dx. Okay. Now I need to take this small area, and let's call it A2. A2. And A2 is the integral from 2 to 3. Integral from 2 to 3 from the parabola. So it's just x squared minus 2x dx. So that's an easy one. So this is some number. And then we want the integral, thirdly, we want this area. We want this area, which is A3. And A3 is also the integral. It's the integral from 1/2 minus root 5 over 2 to 0 from x squared minus 2x dx. All right, so you got 3 integrals. They're all calculatable. Yeah, so for the first integral, you would need to use the substitution. But in general, I hope you understand the method. I don't want to spend any more time on this problem. It's more harder than I anticipated. I've modified the problem, but didn't realize that it involved so many intricate calculations. Integrate A1. Okay, I will show you how to integrate A1 because A2 and A3 are easy, right? So A1 is square root integral of square root of x plus 1 dx. And let's just, for simplicity, take it from A to B, because it doesn't really matter what the limits are. You just substitute them in. You break it into 2 integrals. So it becomes integral from A to B of this thing, x plus 1 dx. Okay, you know what? Let's actually do the limits. Sorry, I'll probably regret it, but minus root 5 over 2 and 3. All right, yes. You break it into 2 integrals plus the integral of 1 dx. I'm just gonna drop the limits for now. But for this integral, you do a substitution. you do a substitution. X plus 1 is u, and then you differentiate du dx. Well, if you differentiate u, well, that's just going to be 1. And that means that du is equal to dx. So the integral becomes the integral of square root of u du. However, the limits have changed because you've introduced u is x plus 1, so you need to add 1. So it becomes from 3 over 2 minus the root 5 over 2 to 4. Limits have changed. So u1 is x1 plus the limit, the lower limit. The lower limit is plus 1, right? And then u plus, and this one is just 1/2 minus root 5 over 2 to 3 of 1 dx. And then you just integrate. So this is going to be u to the power 3 over 2 divided by 3 over 2 between limits 3 halves minus root 5 over 2 to 4 plus just x from 1/2 minus root 5 over 2 to 3. Does that help? I don't know. Your name, sorry, GS. The limit changed because you've changed. You're now integrating with respect to u, not with respect to x. And if x is 3, then u is x plus 1, so u is 4. You've changed the variable of integration. We'll do more. We'll do more later, but I didn't expect a substitution here, so that's why I'm quite reluctant to spend more time on this. Anyways, use a definite integral to find the area of the upper left quarter of the circle of radius 2. So we have a circle of radius 2 x, y, and this is like this. Now, we know that the equation of a circle of radius 2 is x squared plus y squared is 4. That means y is equal to plus or minus square root of 4 minus x squared. But obviously, that would mean that it's plus because y is positive. It's not negative. Negative is this bit. So y is square root of 4 minus x squared. So that's your graph. And you want the area. So you're looking for the integral from 0 to 2 of square root of 4 minus x squared dx. Now here, I'll do a substitution properly and without, yeah. So when you do a substitution, I advise you to draw a vertical line. I draw a squiggly line. And I say substitution is u. Now, this is going to be a little bit surprising because, okay, before I do the substitution, I need to explain why I do the substitution. Otherwise, you'll say, what? So 0 to 2. I don't know the integral from 4 minus x squared, but I do know the integral of 1 minus x squared. So what I'm going to do is I'm going to take the 4 out of this expression. So I'm going to take 4, square root of 4 out, and it becomes 1 minus x squared over 4 dx. And I can take the square root of 4 out as a 2 in front of the integral because the integral is linear and I'm allowed to take stuff out. Minus x over 2 squared dx. Now I'm allowed to use this substitution, this integral, because some integrals you just need to look up. What do you think my substitution is? Can somebody guess my substitution? Compare the two integrals. U is x over 2, exactly. U is x over 2. It's my substitution. So now I differentiate du dx. Du dx is just going to be a half. So if I differentiate this expression. And now I multiply both sides by dx and by 2. So I get 2 du is equal to dx. Right, so dx will be replaced by 2 du. This would be replaced. And then the lower limit, so u1 is going to be 0 divided by 2. So that's 0. And u2, the upper limit, is 2 divided by 2. That's going to be 1. So now my integral becomes 2 multiplied by the integral from 0 to 1 square root of 1 minus u squared. And then dx is 2 du, so multiplied by 2 du. And once again, I'm allowed to take the 2 out. So it's going to be 4 multiplied by square root of 0 to 1 square root of 1 minus u squared du. And then I'm allowed to use this result because so it's going to be 4 multiplied by 1 half u square root of 1 minus u squared plus arc sine u between limits 0 and 1. So now I just substitute 1. And this is 4 multiplied by, open bracket, 1 half multiplied by 1 multiplied by 0 plus 1 half multiplied by arc sine 1. And then minus 1 half 0 times square root of 1 minus 1 half arc sine 0. Arc sine 0. We know that arc sine 1 is pi over 2, and arc sine 0 is 0. And therefore, it's 4 multiplied by, so that's 0, that's 0. So that's pi over 4. 4 multiplied by pi over 4, which is just pi. That's a beautiful result. And what do we expect from a circle? Well, area of a circle of radius 2, area of a circle is pi r squared, which is pi multiplied by 2 squared, which is 4 pi. And a quarter of a circle, is just going to be pi. And ta-da, we got the same result. Probably the hardest way of calculating the area of a circle that you've encountered so far in your life, but very nice. Okay, so that's how you do it. Once again, sometimes you don't just integrate straightforward. You sometimes need to look up integrals because integrals are difficult. This is one of the table integrals that you will be given if you're ever need to do this integral. You won't be given this standard result, so don't worry. You're not expected to do it by yourself. Or they won't tell you the substitution that you need to use. I honestly don't remember how to prove this expression, but I probably, if I sit down for half an hour, I could probably figure it out. You'll need some kind of trigonometric substitution. Right. 4. Find the area of the region enclosed between the curves. Determine whether the origin lies in this region. Well, 12b. Assigned 12b. Same. You just your substitution is going to be x over r. Sub x over r. Right. Okay, so you have some curves. I'm just wondering if we can. 4 minus x. So that's 4, 4, 4 minus x. It's a straight line like this. X plus 4, so that's like this. Y equals x plus 4. Y equals 4 minus x. And y equals x squared minus 4. So x squared minus 4 goes like this. And 2, 4, 2, 4. And it just goes like this. Okay. Well, what would you do here? You need this area. You need this area, and the origin does lie in that area. Yeah, you would integrate. You need to find these points of intersection. So to find point A, so you intersect the two curves. Your y equals 4 minus x. Y equals x squared minus 4. So 4 minus x equals x squared minus 4. X squared plus x minus 8 equals 0. It's not going to be pretty. It's going to be x plus a half squared equals 8 and a quarter, so it's 33 quarters. So x is a half minus a half plus or minus. Well, plus, because we don't need the minus. Half plus root 33 over 2. Okay, so that's the point. That's the right boundary. So minus a half plus root 33 over 2. And now the left boundary, find the left boundary to find B. Find B, we need y equals x plus 4 and y equals x squared minus 4. X squared minus 4 equals x plus 4. X squared minus x minus 8 equals 0. So x is a half minus root 33 over 2. Okay. And the area is the integral from a half minus root 33 over 2 to 0 of it's going to be a bit okay from 0 of x plus 4 dx plus the area of this, so under this graph, plus the integral of it's from 0 to 1 minus a half plus root 33 over 2 of 4 minus x dx plus, now we need to be careful. We need the integral. So from this to 2, basically we need to find, so what we have found this area. So now we need to subtract this area. So that will be no. We don't need that. It's an area between two curves. It's from -1/2 to 0. We subtract the bottom curve minus x squared minus x squared minus 4 dx, like this. You're allowed to do this because it's the area between two curves. So you do top curve minus bottom curve, right? And that's way easier. And then you do minus a half plus root 33 over 2. So no, vice versa, from 0 to minus a half plus root 33 over 2. And then that becomes the top curve. So 4 minus x, that's the top curve, minus the lower curve, which is x squared minus 4 dx. And then you can calculate those integrals. They're quite simple integrals to calculate, so I'm going to stop here. It's just a lot of calculations. All right, I hope that makes sense. Moving on. Evaluate cosine. So this is where we shine with our substitutions. Okay, so the substitution, the obvious one, is that u must equal to 5x minus 2. We differentiate du dx straight away, and that becomes 5, because the derivative of that is 5. So dx is du divided by 5. So the integral becomes the integral of cosine u multiplied by du over 5. The 5 comes out, so it's 1/5 integral of cosine u du. Now we know the standard result that the integral of cosine x dx is sine x plus c, and that means it's 1/5 sine u plus c. And we do, and u is 5x minus 2, so it's 1/5 sine 5x minus 2 plus c. Very easy, very straightforward. Well, very easy compared to the stuff that we've done before. Right. Now let's get to the interesting parts. We've done 5 so far. Evaluate the definite integral. So here you have to use integration by parts, and integration by parts. And the integration by parts looks like this. The integral of u v dash dx is equal to uv minus the integral of u dash v dx. And the part that you need to learn how to do is to choose which one of them. So this one of them is u, one of them is v dash. So I'm going to say that this one is u, this one is v dash. There is a certain rule of choosing which one's which. But yeah, okay. So u and v dash, and I'm going to integrate that. So if u is x squared, that means u dash is 2x. If v dash is sine x, then v is minus cos x. And so the integral from x squared sine x dx, because this is u and this is v dash, can be written as x squared multiplied by negative cos x minus the integral of u dash, which is 2x, multiplied by v, which is minus cos x dx. And this is between limits 0 and pi again. Okay, so that becomes minus x squared cos x minus, no, plus 2 x cos x dx from 0 to pi. And this is also from 0 to pi. But then we see that this is another integral by parts. So we integrate by parts again. By parts again. So the integral of x cos x dx. So this is u, and this is v dash. So that means if u is x, u dash is 1. If v dash is cos x, then v is sine x. So that would be x multiplied by sine x minus integral of 1 multiplied by sine x dx. So this is minus x squared cos x from 0 to pi plus 2, and then x sine x, also from 0 to pi, minus 2 multiplied by the integral of sine x. The integral of sine x is minus cos x. So minus x squared cos x plus 2x sine x and plus 2 cos x. And everything is between 0 and pi. And we substitute pi in. We get minus pi squared times negative 1 plus 2 times pi times 0 plus 2 times negative 1 minus, substitute 0 in, and it's going to be plus, 0, and then minus. I think so. Plus 0, plus minus 0, and then minus 2 times cosine 0 is 2 times 1. So that is pi squared and minus 2 minus 2. So that's pi squared minus 4. Okay. Value the definite integral. So integration by parts in two different formula. Well, it's just different notation. It's not really a different formula. It's the same formula. There are variations. So you can write u v dash dx is equal to uv minus integral of u dash v dx. That's one way of writing it. That's the standard way of writing it. You could write integral of u, well, v dash is dv dx multiplied by dx equals uv minus integral of u, du dx times v dx. Or the advanced version where you can cancel out the dx's. If you cancel out the x, you cancel dx, then it becomes the integral of u dv equals uv minus integral of v du. This is my preferred way of writing it. The problem with this method is just it's very difficult to explain what dv is. Like, what do you mean by dv? Because what is d sine x, for example? Well, to answer this question, what is d sine x is what? Well, you can do d sine x dx multiplied by dx, right? So you divide by dx and multiply by dx. And then you know the derivative of sine x is in fact cos x dx. Oh, so d sine x is simply cos x dx. So once you understand what this means, what is d sine x, then you can use that third formula. I'm not sure. I'm not sure it's very beneficial for you to start using it at the moment. You will get to use it a little bit later in life, but yeah. Okay, so let's move on. Oh, where's problem 8 and 7? What happened? Ah, here they are. Yeah, this one, the last one. Okay, that's really nice. Okay, find the following integrals. Okay, so these are the integrals with sines and cosines are probably one of my favorites because if you take the integral of sine squared x dx and you take the integral of sine cubed x and sine to the power 4x dx, they look very similar, but they have two completely different ways of solving. Like they're not even related, right? So completely different integrals. So odd powers of sine and or cosine, and even powers of sine and cosine have two different methods. So here, with even powers, you would use something that is called power reduction. And here, you would just use a substitution. Here, we have an even power and an odd power. So the total power is odd. And this tells what? No, not total power. Total power doesn't matter. We take the lowest power. Uh, no, if one of them is, well, there are different scenarios. I can't. It's hard to label them all. But if one is odd, the other one's even. We use substitution. If both of them are even, we use power reduction. If both of them are odd, what do we do? Both of them are odd, we do power reduction. Okay, so yeah, it kind of works out. So what is power reduction? Well, substitution is seen. The power reduction is these two formulas. So sine squared x can be written as 1/2 minus 1/2 cos 2x. And cos squared x can be written as 1/2 plus 1/2 cos 2x. So these are called power reduction formulae. Okay? Because you go from sine squared to cosine without a square. Yes. And it's very easy to prove, but never mind. Calculate the following integral. So here we have a power of 4 and a power of 1. So this tells me that I have to use a substitution. So for a, the substitution is u equals sine 2x. I don't have time to explain why sine 2x, but it's the opposite of the odd power. So if cosine is to the odd power, that means we have to use sine. That's just how it works. And you'll see magic happening. You'll see why I use this substitution. Because now I can say du dx, I differentiate that, and that becomes 2, using the chain rule, 2 times cos 2x. Aha, so I kind of, you might see a clue here. And now du divided by 2 cos 2x is equal to dx. So I've expressed dx, so now I can substitute dx into this expression. And now what to do with sine of to the power 4 2x? Well, sine 4 2x. I use trig identities. I know that this is sine squared 2x squared. And when sine is 1 minus cos squared 2x squared. So it's 1 minus u squared. What? Sorry. What am I doing? It's actually simpler than I thought. No. Sine to the power 4 2x is just u to the power 4. No, we don't need to do anything here. So it's u to the power 4, and then it's cos 2x multiplied by dx, and dx is du divided by 2 cos 2x. And here's where the magic happens. Cos 2x disappears. And we're left with 1/2 u to the power 4 du integral. And that is 1/2 u to the power 5 over 5 plus c. So it's 1/10 u to the power 5 plus c. So it's 1/10 sine to the power 5 to x plus c. B, x squared square root of x plus 3 dx. And here the substitution is like this. Sub u equals x plus 3. Easy one. Because now I can differentiate du dx, and that's just 1. And that means du equals dx. So I can just replace dx with du. And that becomes u minus 3 squared, because x is u minus 3. U minus 3 squared, and multiplied by square root of u multiplied by du. I open the brackets, so u squared minus 6u plus 9 times u to the power half du integral. And then I open the brackets again, so u to the power 5 over 2 minus 6u to the power 3 over 2 plus 9u to the power half du. and we integrate that. So that becomes u to the power 7 over 2 divided by 7 times 2 minus 6 multiplied by u 5 over 2, 5 times 2, and plus 9 times u 3 over 2 divided by 3 times 2 plus c. Now reverse substitution. So it's 2/7. Is it x plus 3? Yes. 2/7 x plus 3 to the power 7 over 2 minus 12/5 x plus 3 to the power 5 over 2 plus over 3, so that's 3/6 x plus 3 over 2 plus c. That's it. Okay, finally 7, 8. Lost 8. Okay, getting to the interesting part. And we have a pyramid. We have a pyramid that looks like this, square base pyramid. Okay. And now it has a base A and height h. Now, what I'm going to do is I'm going to twist it on the side. So I'm going to put the pyramid sideways. And I'm going to place the height as long the x-axis, and this is the height, and this is the pyramid. This is the pyramid, and this is y. So this would be a over 2, a over 2. This is minus a over 2. So basically, it's a pyramid turned on the side, and I'm looking at it from the back. So I hope you understand what this means. So now I'm going to cut the pyramid into slices like this. And each slice, so if you take one slice, which is a very thin slice, so it's a thin slice, it is a it has this shape. It is a cuboid. It is a cuboid. So you can think of the pyramid as being made of cuboids of smaller and smaller size, right? You know, like the children's toy where you have a big circle, smaller circle, like a pyramid. Let me see if I can children's pyramid. Yeah, something like that, right? Obviously not, but you can think of the pyramid as made of slabs. Okay, so taking one such slab, we can say that the height is dx, so the width is dx. That's the width. And the size, well, that's just y. That's 2y. The size is 2y. And well, this width is also 2y. All right. Now, to find y is the equation of that straight line. So volume of the slab is going to be 2y squared multiplied by dx. And y is the equation of that line. The equation of that line, y is equal to a over 2h times x plus a over 2. with a minus. Minus a over 2h over x, because that's the gradient. The gradient is a over 2 divided by h, so a over 2h times x, and the y-intercept is a over 2. So that's the equation of the straight line. And yeah, so we can substitute that in. So volume of the slab is dV, is a small volume, dV. So dV is equal to 2y squared times dx. So dV is 2 multiplied by minus a over 2hx plus a over 2 squared. Oh no, the whole thing is squared times dx. So we can open the brackets. So dV is minus a over hx plus a squared dx. Can we open the brackets? I think we should. So that's going to be a squared over h squared multiplied by x squared minus 2 multiplied by a over h times x times a plus a squared dx. And now we can integrate both sides. Integrate both sides. So the integral dv is equal to the integral. Now here, because x changes from 0 to h, 0 to h, that's how x changes. So the starting value is 0, final value is h. And now bear with me. When x is 0, the total volume of the pyramid up to that point is also 0. And by the time we get to h, the whole volume of the pyramid is v, which is the final volume. That's why the limits for dv is going to be from 0 to v, and this is from 0 to h. And then we can just put this in. So it's a squared over h squared, x squared plus 2a over h, 2a squared over h x, that's a minus, plus a squared dx. And now we can finally integrate that. So the integral of 1 dv is just going to be v between limits v and 0. That's just v. I mean, it's v minus 0, so it's just v. And is equal to, and now we integrate that. So it's going to be a squared over h squared times h cubed over 3 minus 2a squared divided by h multiplied by h squared over 2 plus a squared h minus 0. Because if you substitute 0, it's just 0. So the volume of the pyramid is h squared cancels. So a squared h over 3. 2 cancels out, h cancels out, minus a squared h plus a squared h. That cancels and is equal to 1/3 a squared h, which is absolutely true because we know that the pyramid with a side A is volume is 1/3 base times height, so 1/3 a squared times h. So how about we found something really easy in a really complicated fashion, and supposedly we are very pleased with the result. We're pleased that we found the correct formula. Okay, and final question about a water tank. Well, it's not a water tank; it's a water dam, and we have water dam profile. image. Okay, so what we're trying to do is we can see that the water exerts pressure on the wall, and the deeper you go, the more pressure there is. So you can see that the pressure increases with depth, and the pressure is rho GH. It's the pressure at any given depth. We also know, so if we take the wall, if we take a small part of that wall, let's call it DH. DH, that's the width of that. And this is from 0 to H. Oh, DX. Let's say DX. And this is the x-axis. This is the x-axis. We take the small slab. So the pressure at this point, at this height, is, well, so this is x, sorry. Pressure is rho gx, because x is the distance from 0. So we have our x-axis going from x-axis is from 0 to h. Okay, and h is the depth of the water. The width, so area is going to be the width W, because we know that the width of the dam multiplied by dx, because that's the height of that rectangle. So we're looking at a small rectangle of a dam of the wall, and we were interested in the force. And force is pressure times area. Thank you. Thank you, Luke. That's very insightful. Yes. Let's do it the other way around, of course. X is the depth. So we go down this x-axis. Sorry, and this is 0, and this is h. So x is depth. Pressure is rho gx. Yes, and area is W, is still W times that. Yes, so this is a wall. This is a dam. And then, okay. So now force is equal to pressure times area. So for dF, so dF is the force on the thin rectangle. So dF is equal to the pressure, which is rho gx, multiplied by the area, which is W times dx. And then you can integrate both sides. Force, well, when x is 0, the force is 0, because we haven't calculated. So we're kind of filling up the wall. We're calculating the force on each slice. So we're adding up on all the forces. So from 0 to F, where F is the total force, dF, is the integral from 0 to H, because that's the largest depth, rho g x w dx. And now we can integrate that. So rho gw comes out. We get 0 to h, and then x dx, which is rho gw x squared over 2 between limits 0 and h. So that's simply rho gw h squared over 2. And that's equal to the force. Total force is rho GWH squared over 2. And you can calculate it for a large dam, which would be absolutely immense. Okay. Wow, that was fast. So the idea is you take a thin slice of the wall, And because you know the depth at which, so you can assume every part of that thin slice of the wall experiences equal pressure because it's very thin. So pressure doesn't increase. Pressure between the top of this rectangle and the bottom of the rectangle is really small, and that's the reason why you can use that formula. Okay, I'll finish here. So enjoy the assignment. It's a really fun topic. Maybe the problems are actually easier than the ones that I've been doing today. So hopefully, you can manage them without any difficulty. So I'll see you all next week actually, because the next webinar is on the 28th of January. All right, see you.